Hello everyone, let's revise motion in one dimension. To describe motion accurately, we use physical quantities. These can be broadly classified into scalar and vector quantities. Scalars have only magnitude, while vectors have both magnitude and direction. Examples include distance and speed for scalars and displacement and velocity for vectors. Understanding the difference is crucial because motion is often influenced by how much and in which direction. A scalar quantity is described entirely by its numerical value or magnitude. No direction is involved. For example, distance, speed, mass, length, area. All these are scalar quantities. If I say the car traveled 5 kilometers, that tells us how far but not in which direction. Scalars are simpler to work with, but they don't give the complete picture in motion analysis. A vector quantity has both magnitude and direction. This means it tells us not only how much but also where. Examples: is distance a vector quantity? No. Displacement is a vector quantity. Is mass a vector quantity? No. Weight is a vector quantity. Is speed a vector quantity? No. Velocity is a vector quantity. Here we have an example. A person travels from A to B, then from B to C, C to D along different roads. Adding up each part, 5 kilometer, 2 kilometer, 4 kilometer, gives us the total distance traveled, which is 11 kilometers. Distance measures the total path covered, regardless of direction. It doesn't matter how twisty or indirect the path is, we just add up the lengths. In contrast, displacement is the shortest path between the starting point and the ending point in a specific direction. In this example, instead of following the winding route, we measure the straight line distance from point A to D. This gives us a vector quantity, magnitude plus direction, showing the most direct change in position. Let's compare the two directly. Distance is the total length of the actual path traveled. Displacement is the shortest straight line distance with direction. Distance is a scalar quantity, whereas displacement is a vector quantity. Distance can be specified only by magnitude, whereas in displacement we need magnitude and direction both because it's a vector quantity. SI unit is meter. Also, it's meter for displacement. Yeah, both are measured in meters in the SI system, but they can be very different in value depending on the path taken. Here is another example. If you travel around a square from point A to point A, from point A to point A, let's see. Your distance is the total perimeter traveled, 20 kilometers, but your displacement is 0 because you end up exactly where you started. This highlights how distance and displacement can differ drastically. In this graph, the red dotted line represents displacement, the direct line between start and finish, while the blue dot, that represents the actual distance traveled. Displacement is always the shortest possible route between 2 points. So this helps us visualize the difference. Here we see another scenario. AB to BC is the actual distance, and the red path is the displacement. This is a straight line, shortcut between starting and ending points. Numerical value shows that displacement is less than or equal to distance, and only equal when you travel in a perfectly straight line without changing direction. Yes, displacement can be zero even if you have traveled a certain distance. In this example, the path forms a closed loop. We start and end at the same point. The total distance traveled is not zero, but displacement is zero because the change in position is zero. This is a key difference between distance and displacement. Yes, the displacement can be negative. The sign of displacement depends on the chosen reference direction. If we define motion to the right as positive, then motion to the left is negative. Here we start on the right and end on the left of the origin. So displacement has a negative value. This negative sign tells us about direction, not magnitude. Speed is the rate at which a body covers distance over time. It's a scalar quantity. Speed is equal to distance divided by time. This is the formula. The SI unit is meters per second. CGS, centimeter gram second, unit is centimeters per second. So a body is said to be moving with uniform speed if it covers equal distances in equal intervals of time, no matter how small those intervals are. For example, a ball rolling smoothly on a perfect surface without slowing down. Okay, so the formula for distance in uniform speed is, we can find the distance like this. Because speed is distance divided by time, you can say that distance is equal to speed multiplied by time. Non-uniform or variable speed occurs when a body covers unequal distances in equal intervals of time. For example, a ball rolling on a rough surface will gradually slow down, covering less distance each second. Most real-life motion is non-uniform because speed is affected by friction, air resistance, or acceleration. Instantaneous speed is the speed of an object at a specific instant in time. It's found by taking the distance traveled in a very short interval divided by that tiny time interval. A speedometer in a car measures instantaneous speed. Here is the formula. Distance traveled in a short interval divided by time interval. Velocity is the rate of change of displacement with time. Unlike speed, velocity is a vector quantity. It includes both magnitude and direction. Velocity is equal to displacement divided by time. If AB is 3 meters and BC is 4 meters, AC will be equal to 5 meters as per the Pythagorean theorem. AB square plus BC square is equal to AC square. So that's how we would get AC equal to 5 meters. Let's say an object traveled from A to C in 5 seconds. Then its velocity would be equal to 5 meters divided by 5 seconds, which will give us 1 meter per second. SI unit of velocity is meter per second and it's a vector quantity. Uniform velocity means an object moves in a straight line with a constant speed and direction. Magnitude of the velocity doesn't change. Direction of motion also remains the same and there is zero acceleration. Let me again start this animation. Here you can see that the magnitude does not change, direction remains unchanged and there is zero acceleration. Non-uniform velocity occurs when an object changes speed, direction or both. The magnitude may increase or decrease. The direction may change, like turning a corner. The object experiences acceleration, positive or negative. A ball moving around a curve at a constant speed has changing velocity because its direction is changing. So the speed is constant but the velocity is variable or non-uniform. Let's compare speed and velocity. Speed is equal to distance divided by time. Velocity is equal to displacement divided by time. Speed is a scalar quantity and velocity is a vector quantity. SI unit is meter per second and it is the same for velocity. Can speed be negative? No, but velocity can become negative. Acceleration is the rate of change of velocity with time. The formula is acceleration equal to change in velocity divided by time interval. A equal to V minus U divided by T. V is the final velocity, U is the initial velocity and T is the time. So we can rearrange the equation in terms of final velocity. So V will be equal to U plus AT. V equal to U plus AT. SI unit is meter per second squared. CGS unit is centimeter per second squared. And yes, it's a vector quantity. Acceleration is uniform when equal changes in velocity occur in equal time intervals. A good example is a body in free fall under gravity. Neglecting air resistance, its acceleration is constant at 9.8 meters per second squared. For a freely falling object, we can write A equal to G. We can represent motion in one dimension using three main types of graphs: displacement time graphs, velocity time graphs, and acceleration time graphs. These visual representations make it easier to understand trends, calculate quantities like velocity and acceleration, and interpret the real-world motion data. The displacement time graph shows a horizontal line. The displacement stays constant with time, meaning that the object is stationary. It's not changing its position at all. So velocity is 0. Here is another stationary example. The displacement remains fixed at 30 meters for the entire 10 seconds. The flat line on the graph confirms there is no movement. So the slope and therefore the velocity is 0. When an object moves with uniform motion, the displacement time graph is a straight line with a constant positive slope. This slope represents velocity, which remains unchanged. For example, here the object's displacement increases steadily from 0 to 100 meters over 10 seconds. A positive slope means the object is moving in the positive direction. The slope is calculated as y2 minus y1 divided by x2 minus x1. You can pause the video and substitute the values of y2, y1, x2 and x1 to find the slope. So, slope is equal to 80. You can see the y2 coordinate minus 40, the y1 coordinate, divided by 8 minus 4. You can just extend a line like this. You'll find that it is the y2 coordinate, the y1 coordinate, here is the x2 coordinate, and here is the x1 coordinate. So slope is equal to 40 divided by 4. So slope, which represents velocity, is equal to 10 meters per second. This is another example of uniform motion, but here displacement decreases steadily over time, meaning the object is moving back towards the starting point. The slope is constant, so the speed is uniform. A negative slope indicates that the motion is in the opposite direction to the chosen positive axis. Slope is y2 minus y1 divided by x2 minus x1. Substitute the values and you would get slope equal to minus 10 meters per second. The negative sign shows direction while the magnitude tells us the speed in the displacement time graph. This graph shows both positive and negative slopes. From O to A, slope is positive. Slope of OA is y2 minus y1 divided by x2 minus x1. Substitute appropriate values. You would get the slope of OA, which represents the velocity, equal to 10 meters per second. Positive slope from O to A. From A to B, slope is negative. Let's calculate. Y2 minus y1 divided by x2 minus x1. Substitute appropriate values. You will get slope of AB equal to minus 7.5 meters per second. This is the negative slope from A to B. In this case, positive slope means moving forward. Negative slope means moving backward. This graph shows non-uniform motion. The slope changes at different times. In the first 2 seconds, displacement increases slowly. Between 2 and 5 seconds, it increases more rapidly, meaning the object is moving faster. And from 5 to 6 seconds, the slope is even steeper. Therefore, we can say acceleration is happening. Non-uniform motion is common in real life, as speed often changes. In uniform motion, velocity remains constant over time. The velocity time graph is a horizontal line. The displacement can be found by calculating the area under the curve. In this case, we have a line. So if we can find the area under the line, we can find the displacement. So here the velocity is 10 meters per second for the entire 10 seconds. So once again, area under this line would give you displacement. So 10 multiplied by 10. That would give us displacement of 100 meters. When velocity changes at a constant rate, the velocity time graph is a straight line with a constant slope. The slope of this line equals acceleration. A positive slope means acceleration and a negative slope means deceleration or retardation. So, to calculate slope, we need y2, y1, x2 and x1. y2 is 70, y1 is 30, x2 is 7 and x1 is 3. So slope is y2 minus y1 divided by x2 minus x1, 70 minus 30 divided by 7 minus 3. So 40 divided by 4 gives 10 meters per second square, which is the acceleration. So this is uniform acceleration because velocity is increasing at a constant rate. The velocity, however, is non-uniform because velocity is not constant. Even if the graph is irregular, we can still find displacement by calculating the total area under the curve. Here we split it into shapes, triangles and trapeziums and find the sum of their areas. Positive areas are above the time axis and negative areas are below the time axis, showing motion in the opposite direction. Area of triangle ABC is half base multiplied by height. Base is 4, height is 5, so we get area of triangle ABC equal to 10 meters. Area of trapezium CDEF is half multiplied by sum of parallel sides multiplied by height. So the sum of parallel sides is 5 plus 3. See, 9 minus 4 is 5 and 8 minus 5 is 3. And they are separated by 5. So half multiplied by 5 plus 3 multiplied by 5. So this gives us 20 meters. Area of trapezium FGHI, that is half multiplied by 4 plus 2. So 13 minus 9 is 4 and it is 12 minus 10. This is 2. And they are separated by distance of 5 meters. So half multiplied by 4 plus 2, sum of parallel sides multiplied by height, which is 5. So this gives us the area of trapezium FGHI equal to 15 meters. Now displacement of the body is area of triangle ABC minus area of trapezium CDEF. It is below the time axis. Plus area of trapezium FGHI. So add the substitute the values. Area of triangle ABC is 10. Area of trapezium CDF is 20. So 10 minus 20 plus area of trapezium FGHI, which is 15. So the displacement of the body is 5 meters. Now this is a case of uniform retardation or constant deceleration. The velocity is decreasing linearly from 40 meters per second to 0 meters per second over 4 seconds. So area under this line will give you the displacement. So displacement of body in 4 seconds is area of triangle AOB, which is half base multiplied by height. What is the base? 4 minus 0 is 4 and height is 40 minus 0, that is 40. So area is 80 meters. Now let's calculate the slope. Slope of AB is equal to 10 minus 30. See, Y2 is 10 corresponding to this point. And Y1 is 30. X2 is 3 and X1 is 1. So 10 minus 30 divided by 3 minus 1 gives us minus 20 by 2. So the acceleration is minus 10 meters per second squared. Here the body starts with a velocity of 10 meters per second and accelerates to 35 meters per second in just 5 seconds. The displacement is found by finding the area of trapezium ABDO, half OA plus DB multiplied by OD. Substitute the values. The area is 112.5 meters. Now let's find the slope. Slope gives us the acceleration. Acceleration of car in 5 seconds. Slope of AB is y2 minus y1 divided by x2 minus x1. Here y2 is 30, y1 is 20, x2 is 4 and x1 is 2. You can take any values of y2 and y1 along this line. Okay, so we have chosen this. Okay, so 30 minus 20 divided by 4 minus 2, that would give us 5 meters per second squared. This is the acceleration. So the area of trapezium gave us the displacement, whereas the slope gave us the acceleration. When velocity is uniform, acceleration is 0. Again, I am repeating this. When velocity is uniform, acceleration is 0. The acceleration time graph is simply a horizontal line along the time axis. Okay. This tells us that there is no change in velocity over time. So the velocity is constant here, 10 meters per second throughout its journey. So there is no change in velocity and therefore there is no acceleration. It remains zero. In uniform acceleration, acceleration stays constant and positive. The acceleration time graph is a horizontal line above the time axis. Here you can see acceleration is 10 meter per second square throughout the journey. In uniform retardation, acceleration is constant but negative. The acceleration time graph is a horizontal line below the time axis. Here you can see that A is minus 10, meaning that the body is slowing down at a steady rate. For a freely falling body, acceleration is constant. Let's take g as 10 meters per second squared. The acceleration time graph is a horizontal line above the axis. If we calculate the area under this line for each 1 second interval, we can get the change in velocity for that period. So how would its velocity time graph look? This is the acceleration time graph. I want velocity time graph of a freely falling body. So for that I'll be finding areas enclosed between straight line and time axis for each time interval of 1 second. So I will draw lines. I'll find area of this rectangle. Then I will find area of this entire rectangle and so on. Okay, let me explain this to you in the following slide. So here are the rectangles. Okay, now let's find the area enclosed between the straight line and the time axis for each time interval of 1 second. So velocity after 1 second, the area will give us the velocity. Area after 1 second, that is area of this first rectangle that you can see, OABP, that is 10 multiplied by 1. So velocity after 1 second would be 10 meters per second. What is the velocity after 2 seconds? Area of this entire rectangle, O, A, C and Q. It is not PBCQ. It is O, A, C, C, Q. Okay. So that would be 20 meters per second. Similarly, velocity after 3 seconds would be 30 meter per second. Velocity after 4 seconds would be 40 meter per second. And velocity after 5 seconds would be 50 meters per second. The acceleration is constant here. It is 10 meter per second square. We are finding the area. Okay, and the area under this line gives us the velocity. So velocity after 1, 2, 3 and velocity after 5 seconds is 50 meters per second. For a freely falling body, velocity increases linearly with time. So this gives us a straight line. After 1 second, velocity is 10 meters per second. After 5 seconds, velocity is 50 meters per second. The slope of this line will give us the acceleration, and that would be equal to g. And remember, we had taken g equal to 10 meters per second square. So if you find the slope, it would be equal to 10 meters per second squared. How would its displacement time graph look? From the velocity time graph, we can calculate displacement by finding the area under the line for each time interval. For example, in the first second, area would be half base multiplied by altitude. So base is 1 and height is, or altitude is 10. So half multiplied by 1 multiplied by 10 will give us the area of triangle OAP. That is the displacement in 1 second. Displacement in 2 seconds would be area of triangle OBQ. So half base is 2, altitude is 20. So we would get area of triangle OBQ equal to 20 meters. So this is displacement in 2 seconds. Displacement in 3 seconds is 45 meters. Displacement in 4 seconds is 80 meters. And displacement in 5 seconds is 125 meters. See this triangle OET. Okay, O, E and T. So this is half base is 5 minus 0, that is 5, and altitude is 50 minus 0, which is 50. So I will get area as 125 meters. You might be wondering why I have written the unit of area as meter. It is because in this graph we multiply the units. Meter per second multiplied by second gives us meter, not meter squared. That's why. So we have obtained the displacement in 1 second, 2 second, 3 second, 4 second and 5 second. Now let's see how the displacement time graph looks. It would look like this. Okay. So this is the displacement time graph for a freely falling body. These are the standard equations of motion for constant acceleration. The first equation is v equal to u plus at. V is the final velocity, u is the initial velocity, a is acceleration and t is time. It relates velocity, acceleration and time. So here is displacement s equal to half u plus v multiplied by t. This is the displacement from average velocity. Okay, u plus v divided by 2 gives you average velocity. Average velocity multiplied by time gives you displacement. Then we have s equal to ut plus half at square. And finally v square equal to u square plus 2as. Let's now solve a couple of problems. A bike accelerates from rest at 5 meters per second square for 4 seconds. So it starts from rest, u is equal to 0. Acceleration a equal to 5 meters per second square and t is 4 seconds. Find its final velocity. U is 0, a is 5 meters per second square, t is 4. So final velocity can be obtained by using the equation v equal to u plus at. Substitute the values of u, a and t and you will get final velocity after 4 seconds equal to 20 meters per second. Now we need to find the distance covered. So distance covered during the acceleration would be ut plus half at square. S equal to ut plus half at square. We have the values of u, t and a. Just substitute these values. You will get s equal to 40 meters. So this is the distance. Now for the deceleration phase, this final velocity will be the initial velocity. So the bike will be applying the brakes and eventually it will stop. So the initial velocity with which the bike is going is 20 meters per second now, and the final velocity will be 0. And if it decelerates uniformly to rest in 4 seconds, so time is 4 seconds again. So now let's find the deceleration. V equal to u plus at. Rearrange this equation in terms of a, or you can substitute the values. If you rearrange in terms of a, it would be v minus u divided by t. So you will get a equal to minus 5 meters per second squared. Distance covered during deceleration, again use the equation ut plus half at square. We will take initial velocity as 20 meters per second in this deceleration phase. So 20 multiplied by 4 plus 1 by 2 multiplied by acceleration, which is minus 5, multiplied by 4 square. So the answer is 80 minus 1 by 2 multiplied by 5 multiplied by 16. So 80 minus 40, that would be 40 meters. A bus moves at 20 meters per second for 6 seconds. Okay, so first the bus is moving at a constant velocity of 20 meters per second for 6 seconds. And then it accelerates uniformly to 32 meters per second. Now the new velocity, the final velocity is 32 meters per second in the next 6 seconds. Okay, find the total distance covered in these 12 seconds and find the acceleration during the last 6 seconds. Okay, let's first obtain the distance covered in the first 6 seconds. So first phase is constant speed or constant velocity. So u is 20 meters per second, t is 6 seconds, velocity is constant, so no acceleration. So s equal to ut plus half at square, is 0, so directly I can use s equal to ut. So u is 20 and time is 6. So the distance for the first 6 seconds is 120 meters. For the second phase, when it starts accelerating, okay, it accelerates uniformly, and the new velocity, which is the final velocity, is 32 meters per second. So now u is 20, v is 32 meters per second, and time is 6 seconds. So it accelerates. Okay, so S2 is equal to u plus v by 2 multiplied by t. Okay, so this is average velocity. U is there and v also has been given to us. Okay, so we will take the average velocity multiplied by time, which is 6 seconds. So 20 plus 32 divided by 2 multiplied by 6, 52 divided by 2 multiplied by 6 will give us 156 meters. So the total distance covered, this was in the first 6 seconds and this was in the 6 seconds following these. So total is 12 seconds. So the total distance is S1 plus S2, which is 120 plus 156, which is 276 meters. Now we need to find the acceleration during the last 6 seconds. Okay, so A is equal to V minus U divided by T. Okay, V is equal to U plus AT, and if you rewrite the equation in terms of A, you will get this, A equal to V minus U divided by T. So V is 32, the final velocity, U is the initial velocity, which is 20, and time is 6 seconds. In both cases, time is 6 seconds. So in 6 seconds, it accelerated to 32. So on substituting the values, we will get the acceleration equal to 2 meters per second squared.